you very much, Professor Cherner, for introduction. And first of all, I'd like to thank also the organizing committee that gives me the opportunity to talk a little bit about our work. And contrary to previous speakers, this is just an applied study, material study in which nuclear magnetic resonance is one of the very powerful, but one of the methods that used for characterize rather complex materials. Some information about support of our research. And at the beginning, I'd like to talk somewhat about what the lights are, because I know that among the participants are students, PhD students. They maybe not everybody are familiar with these kind of materials. So just few words. So to imagine what are 3D zeolites, I start from 3D zeolites. It's very useful to imagine the structure of silica, or that can be informed, for example, of quartz, crystalline silica, or amorphous silica. What it is, it's just the network of 3D network of CO4 tetrahedron that joined to each other by the oxygen in the corner. And if you substitute, for example, one or several silicon cations with charge 4+, for aluminium 3+, just to keep the charge balance, you need to introduce another cation, for example, with, protons or sodium or potassium and so on. And this substitution leads to formation a very, very interesting porous structure, and that called zeolites. And this porous structure are ordered with ordered porous structure. By now, there are more than 230 known framework zeolite structures. And for more details, you can see the very nice database prepared by International Zeolite Association. And if you look at this different zeolite framework, we can see that they are very, very different. Why they are different? First of all, they're different because of the C to aluminum ratio. Because, for example, there are several structures that are stable, for example, for very, very small concentration of aluminum, or there are some structures that are stable within a very large range of the C to aluminum ratio. And the main difference, maybe, of these different zeolite frameworks is the structure of channels, because the channels can be of different shape, different dimension, for example, 1D, 2D, 3D, different size, and so on. And of course, we can introduce different cation and molecules inside. So there is a big variety of different porous structure. Maybe the most known application of zeolites is molecular sieves, because the pores or channels of zeolite structure are of the well defined for shape and size. It means that depending on the zeolite type, several molecules may penetrate inside, but the other not. For example, you can see here an example of such a dependence of the zeolite structure, different zeolite structure. These three letters abbreviation corresponds to specific zeolite type. And the correlation between this structure, the shape and size of this pore opening, and here there is a list of several molecules that can penetrate inside. And so another picture is given here, for example, that we can see that the typical size of this pore can be, for example, 5.8 angstrom, 6.5, 7.2, and so on. Another very important application of the zeolites is their use as catalyst, because the inner surface of these porous materials are very rich of different acid sites, different type. Moreover, we can introduce inside different cations or clusters or molecule or nanoparticles and so on that are immobilized inside the structure, and so we can use this new material for specific catalytic reaction. But there are, of course, some limitations of 3D zeolites. As I told, the pore diameters is normally restricted by 10 angstrom. So only small molecules may go through. It means that the catalytic reaction we want to force by these materials is rather limited because of this limited size. Moreover, the mass transport is also low because of pore size limitation. In addition, now it's very popular to functionalize the porous materials, the surface, and also there are some limitations in these zeolites. So how we can get with this problem is to create, for example, the so-called mesoporous zeolites or zeolites with hierarchical porosity. And there are some classifications that is approved by EUPAC. This is International Union of Pure and Analytic Chemistry, I think. For example, that micropores, it means that the pore diameter is lower than 2 nanometers. So all 3D zeolites, they are normally microporous zeolites. Mesopores, this is the pore size between 2 nanometers and between 2 nanometers and 50 nanometers. And macropores is with larger diameter, pore diameters more than 50 nanometers. And here I moved closer to the subject of my presentation, is what are the 2D or layered zeolites, or pillar zeolites. So the pillar zeolites or the layered zeolites, they consist of zeolitic layers that are normally about 1 nanometers. In fact, maybe one unit cell, and which are stuck together either just as monolayers that are stuck together, or maybe separated by organic molecules. There are several routes for fabrication of these materials, and I will talk about the materials that were synthesized by our colleagues. And these are materials that are synthesized in presence of by self-assembling methods and presence of organic structure-directed agent. So So the main goal of our study is in fact to obtain new materials for catalysis, and not only with improved properties. It means develop surface, new catalytic sites, and so on, and involve synthesis of these new materials, their characterization, and comprehensive study of these properties. And for this characterization, we use a large variety of different techniques. XRD, electronic microscopy, thermal analysis, and of course, NMR. Now, a few words about the preparation, because it's important for following slides. The preparation of these materials includes four steps. First is the self-assembling growth of lamellar layered 2D zeolites in presence of so-called organic structure-directed agent, and in our case, this is the acetyl-trimethylammonium bromide. Also, we add polyethylene glycol, and for one structure we use only CETA-pipette, and for another, for the same structure of the lights, we use also the tetrapropylammonium bromide. Here, this is the picture of these molecules. And after we fabricate these layered lamellar zeolites, we introduce TELs, tetraetoxysilane, or TELT, with titanium in the center, the same molecule. Then hydrolysis occurs just to form either CO2, either TO2 oxides between these layers, and calcination to evacuate the organics. All the samples were synthesized by our colleagues in Center for Nanoscience and Nanotechnology in UNAM in Mexico, but all the studies were carried out at our university. So as soon as the materials is rather complex and the preparation steps are also involve several procedures, we use rather complex approach to study these materials. In fact, can be divided in several steps, also just the characterization. First, of course, we need to characterize the composition, the structure, the thermal properties. Then we study it's more profound. We study the morphology, topology, thermal properties as well, but in more details. And after that, after we know something about materials, at least it is really the pillar zeolites, we can use the other methods for more profound, more fine analysis, including, for example, the study of composition, but using NMR with space, local structure, but using NMR, whole-gas interaction, so on, so on, so on. And finally, we need the final goal is to test the properties, the target properties, and to propose the materials with better or even optimal properties for concrete application. So, as I told, all the samples were studied at the research park of our university in different research centers. They are listed here. And so I will start from the studies of 2D zeolites with two pillars: structure, morphology, and composition. So, as I told, we need to understand first to test that we really have the materials that we want to study. And the main questions are: what are the structure of the zeolitic layers, inner surface, aluminum sides, how perfect it is, what is the structure and dynamics of the organic molecules. and of course the gas-host interaction between the inorganic zeolite layers and organic molecules or other molecules like water. And to respond to this question, we use nuclear magnetic resonance. So here some result of the preliminary of this preliminary study of the synthesized materials, the structure using the XRD, and not only XRD but small angle X-ray scattering, as well as morphology studied by scanning electron microscopy, and composition studied by energy dispersive X-ray spectroscopy, and thermal analysis. So first of all, when we look at the XRD pattern, we can see that the synthesized materials exhibit typical features of the corresponding 3D zeolites with a smaller, with an amorphous halo between in this region between 17 and 30 theta degree. This is rather typical for this kind of materials, and so for us, what is important is that we have really the mordenite structure, the targeted, or the ZSM5 that is called MPI structure. But how to prove that we have 2D zeolites? To respond to this question, we need to look in this small angle region. And here we can see that there is a peak, an additional peak, that corresponds to the 1 or to the 001 lamellar structure. So it really, we have synthesized the 2D materials with interlay space of about between 3 and 4 nanometers. And the layer, this zeolitic layer, is about this zeolitic layer is about 1 unit cell. It's about 9-10 angstrom. In the pillared materials, it means after calcination, we can see that we also observe this small peak that confirm that we deal with pillared materials, with layered materials. I think, okay. So very important to understand the morphology of these materials, and to understand how this calcination, this rather strong procedure. I remind that the calcination occurs at for 4 hours at about 550 degrees C, in how this procedure affects the morphology. And we can see that as synthesized samples, they are elongated plates up to 1 micrometers in length and about 0.1 micrometers in width, combined in stacks. And the pillaring, that means calcination, does not change noticeably the morphology of these zeolites. It's also very important for future applications. Here, maybe it's not so spectacular for NMR people, but nevertheless, it's quite interesting to follow how the composition of the sample occurs. But I think I can skip this slide. And if you look at the composition of these compounds that made by ADX spectroscopy, we can see that before calcination, it means the sample is synthesized. They contain a lot of sodium, because sodium here, the ratio of sodium to aluminum is about 1. It means that sodium plus is the charge compensating cation in these materials, and both CTAP and tetrapropylammonium bromides present in the cationic form, balancing the dangling bonds of the zeolite layers. However, in the pillar materials, the sodium to aluminum ratio sharply decreases. It means that the role compensating cations should eventually pass to protons. And the increase of this silica to aluminum ratio means, you see twice, it's doubled, means that CO2 pillars are formed. Now, let me tell about NMR study of the synthesized materials. As I told at the beginning, these materials were prepared by self-assembly method, and here 2D layers of zeolite are separated by organic molecules, by, for example, CETA. And here you are the proton in carbon NMR spectra, mass NMR spectra of the MPI and mordenite zeolites. They exhibit more or less similar features. First of all, we can see the same all the peak that corresponds to the molecules, yes, but they are broadened due to interaction, due to strong dipole-dipole interaction, because these are molecules confined in solids, and their mobility is restricted. Also, very interesting peak is here. It's the peak of C3 of tetrapropylammonium bromide, because this molecule is introduced into the mixture, into the soap to prepare these materials, especially to form the specific MPI structure, porous structure, because MPI have a very specific porous structure, and here the splitting of this C3 peak means that these molecules is inside the pore of this zeolite. By this pore have different channels in this direction and in this direction, in two perpendicular direction. So these four C3 carbons have different environments that is reflected here. Also, what is interesting, what we can see here, that both, but especially maybe not only for protons, but for C13 NMR lines, they are broadened when we move from the tail towards the head of the CETA molecules. It means the mobility of these molecules decreases from the head, or decreases from the tail to the head. So if you look in more detail, we can also see here I plot the chemical shift of this CETA carbons versus the number of the chain. So here also we can see that there is there is no strong difference between mordenite and MPI sample, and also the reference data from other publications, but there is some difference between with liquid CETA molecules. And this shift that we observe here for the C1 carbon also points out that there is a strong interaction of this acetyl trimethyl ammonium head with zeolite framework. The same conclusion is confirmed by the experiment using variable contact time with cross-polarization from protons to carbon. Here, there is the intensity of the individual peak as a function of contact time, and once again, we can see from the fitting of these intensities by this equation, and from determining the parameters of this fitting, we can conclude that once again the tail carbons has the greater mobility, as compared to the head. So we can imagine the structure, the inner structure of this layer of the lights as following: that we have the sheet of zeolitic sheet with theta molecules which are alternating with head or with direction in this direction, alternating with head and with this charged head attached to the zeolitic surface. Now, what happens if we introduce tails with further hydrolysis, with formation CO2 and further calcination? So we can see that the introduction of these steps results to essential broadening of the individual lines. Once again, it means the decreasing of the mobility of CDAP molecules. And also, we can see that there is no trace of carbon after annealing. It means the annealing evacuate completely the organic molecules. To study local structure in more detail, we use the aluminum and silicon mass NMR. Let's first discuss the aluminum NMR in this material. In fact, aluminum mass NMR is a rather typical and routine procedure to test the perfectness of the zeolitic framework. As I told, according to the XRD data, we know that our synthesized materials have specific zeolite structure, but we don't know how perfect it is. And here we can see the aluminum signal in morganite and MPI for the SS synthesized zeolites, and you can see that it represents the one line at about 60, exactly 56, 54 ppm. And this line corresponds to aluminum in tetrahedral sites. It means that it corresponds to aluminum framework, from framework, zeolitic framework. The introduction of tails and its hydrolysis, it doesn't affect much the aluminum, just it results to a little broadening of the signal. But the calcination leads to appearing a new line here at about 0 ppm that correspond to aluminum in octahedral sites. So it means that after calcination, aluminum drop out from the framework. Why it happens? So the main logical explanation is that the cetyl-trimethylammonium cations are in the synthesized materials are localized near this aluminum of 4- octahedron. just because this, when aluminum substitutes silicon, it creates negative charge in this place. So it's logical that this cation attached close to this site. And of course, and the removal of the organic cation.
I'm very sorry, but you have only 2 minutes more because we still have 5 minutes for questions.
Oi. I thought that I have more. Okay.
No.
Oh, I thought that I have 40.
2 minutes more. No,
this
is
okay.
already corrected time.
Okay. So we can conclude here. If now we look at the silicon spectra, and follow the evolution upon the preparation step, we also can extract a lot of information concerning that what happens with these materials. For example, at the beginning, we can see that the spectra of the layered zeolites are very the same, almost the same as the 3D zeolites, but with rather important contribution of Q4 with one aluminium neighbor sites and Q4 with 2 aluminium sites, with what we suppose is due to the interaction with setup molecules upon growing. Moreover, using this data, we can also, using this data, we can also extract the information about the real content of the aluminium and real content of the real composition of the silicon aluminum framework. That is in good agreement with data obtained by energy dispersive spectroscopy. Maybe I skip into the detail as I have no more time. Also, only tell that in these materials, the most important and interesting conclusion from these studies is that in these materials, as soon as tails is introduced into the interlayer space, the autohydrolysis occurs. It's a very important conclusion for people who produce these materials, because it's very affects the chemistry of this kind of material.
I'm sorry, you still have 5 minutes, but without questions.
Okay. So maybe a few words about the second part of our studies of my report is about the dynamics, the study of dynamics of water molecules in this interlayer space. So first of all, we characterized the porous structure of these materials. So we can, using the thermal analysis and nitrogen absorption, we can conclude make conclusion about the pore size distribution, pore volume, their form, and so on. So, and by NMR, we can study the dynamics and the dynamics of water molecules and their interaction with the inner space. So it is known that a proton of water chemical shift of water protons is very different depending of does the water molecule is the monomer, bulk water, or interact with surface. So the chemical shift may vary from 0 to about 12 ppm. And here, what we do, we studied the water behavior in interlayer space of pillar zeolites using mechanical screening and cooling down these samples and relaxation experiment, making a relaxation experiment. So briefly, I can tell that our the results confirm that there are different type of water, and there is a very strong interaction with the light surface with different regime that changes upon cooling down. And also from a very temperature dependence of the light width, we can determine the activation energy of the freezing water, of the freezing of the confined water. Using relaxation study, we have obtained a very interesting results because here there is a T1 relaxation time versus inverse temperature, and we can observe at least.
Sorry, you have only 2 minutes more.
What?
You have only 2 minutes without question.
I try my best to go to the finish. So we have at least three different processes. It means that water interacting with the light surface, fast rotation of sticking out water protons, and speed freezing of the bulk water. And by applying the BPP model, taking into account our modifications, including exchange between these different water fractions, we have obtained 3 different activation energy for these motions. And to deeper study one of these local minimum effect, I'm talking about the second minimum, this temperature dependence, we applied the spin locking techniques to shift this minimum in more comfortable temperature region. And once again, we can obtain the more accurate activation energy parameters. I think that I will stop here just to tell about the perspective and current studies. So actually what we do now, we applied NMR and molecular dynamic simulation to study organic molecules in confined space of these zeolites with hierarchical porosity. And also we study we obtained very interesting results concerning the 2D zeolites with other pillars, not only CO2, but with titanium O2. It's a very new photocatalytic materials with very interesting properties. And also we work on the introduction of other oxides. So I think I will skip here. And I'd like to thank you for your kind attention. That's all.
Thank you very much for your presentation.